Hi, everybody. Welcome to the August 2022 SJAA Imaging Special Interest Group meeting. And tonight we're going to continue our series on narrowband imaging. Last month, Alex talked to us about narrowband imaging and described his app for doing that. Tonight, Francesco Meschia is going to talk to us about the why and how of narrowband imaging, and follow it up in a couple months with some examples of processing narrowband imaging. Next month, Julien Lecomte will talk to us a little bit about maker projects for astro imaging. And I want to once again encourage anybody who has some other presentations to make. We would love to hear you speak at one of these meetings. Please send an email to our imaging mailing list or to me directly, and love to hear from you and get you to talk. So without further ado, Francesco, take it away.
Thank you very much. Hi, let me share my presentation. All right. And no. Great. So thank you very much, and good evening to everybody. My name is Francesco Meschia. This is the first of a series of 2 presentations I'm giving about narrowband imaging. And I called this first presentation Why and How, because we're going to discuss exactly that. Why we do narrowband imaging, why is it, has it changed the way that amateurs do astro imaging, and how we capture narrowband data. Tonight, we're not going to talk about processing. The how is the how to acquire narrowband data. So I will start with the definition. So what is narrowband imaging? We call it narrowband imaging a set of techniques. It's not just one. And these are all the techniques that involve the capturing and the processing of images of astronomical objects by using only very small and narrow portions of the visible spectrum of light. And we do that by selecting the portions of the spectrum of our interest using narrow band filters with narrow bandpass windows. So that's why we call it narrowband imaging. It refers to the bandpass of the filters. But how narrow is narrow? So if I put on this slide a chart, I believe I took it from Astronomic, and it's a representation of the visible spectrum and then some. So everything between 400 and 800 nanometers. What we can see with our eyes is essentially the region between 400 and 700 nanometers. Of course, there are individual differences that people can see a little more, and some people can see a little less. But let's say that as an average, we have about a 300 nanometer window in terms of wavelengths of the photons that we can see. When we do what's called broadband imaging, using, for instance, RGB filters or using a one-shot color camera, each of the filters, essentially the 3 filters, divide the spectrum among them so that each filter is roughly 100 nanometer has a 100 nanometer wide window of transmission. When we talk about the narrowband filters, what's commercially available today has transmission windows that go from 3 nanometers to 15 nanometers. So they are several times narrower than a typical RG or B filter. It can be 30 times narrower, or it can be just 5 or 6 times narrower. And there are differences, of course, in what you can obtain with the different bandwidth of the filter. And as a graphical representation, I tried to put here the superimposed to the 3 windows for R, G, and B. I put the 3 transmission windows for 3 nanometer narrowband filters, the oxygen 3, hydrogen alpha, and sulfur 2. Now, oxygen 3 is the shortest wavelength at 500.7 nanometers. H alpha has an intermediate central wavelength in the red region at 656.3 nanometers. And finally, sulfur 2 has a 672 nanometer as a central wavelength. Okay, this is great, but why do we care about this? Why is it important? Why do we like, even though it's not important for us amateurs, to do narrowband imaging? Well, I will start off by quoting our host, Hai, who once said in this forum, why are stars bright? Well, stars give off light because they're hot. They behave essentially like a piece of metal brought to very high temperature. In more scientific terms, they behave like black body radiators, and their emission, the spectral composition of the light they emit, has a continuous spectrum, and it depends depending on the temperature of the star. This spectral composition may have a peak at one wavelength rather than another. For instance, a red star may have a peak wavelength of about 700 nanometers, so it would look red. A yellow star may have a peak wavelength of about 550 nanometers, like our sun, and a blue star could be deep in the blue region, or if it's really, really hot, even in the ultraviolet. So this is the way stars behave. They emit lights at essentially all wavelengths, following the laws that describe a black body radiator. However, not everything in the universe behaves like that. When astronomers started studying the spectra of nebulae in the 19th century, and back then anything that was not a star was called a nebula, they didn't have the perception of what is the difference between what we now call a galactic nebula and what is a different galaxy. Like Andromeda used to be called the Andromeda Nebula until 1920. So they found that some nebulae had a spectrum that resembled a star spectrum, with a continuous distribution of photons in various wavelengths. But other nebulas were radically different, and this is, of course, a modern spectrum that I pictured here. But you see, that is a line type of spectrum in which there is a continuum. It's basically almost a background continuum, but there are very prominent spectral lines. Now, we call them lines just because if you look at them, if you look at the spectrum of a star through a spectroscope, you're going to see a line that represents the slit of the spectroscope illuminated by one monochromatic light, one monochromatic wavelength. But they look like, if you plot them in a chart like this, they look like sharp vertical peaks. And back then, although they didn't understand why, they knew that different chemical elements had a different set of the spectral lines. And they had atlases of spectra for different elements. And as an example, here I have the spectrum of the emission from hydrogen. So if you have a hydrogen lamp, you're going to have one red line at 656 nanometer, which we call H alpha, and then another one, a blue one at 486 nanometer, H beta, and then H gamma and H delta at shorter wavelength. But despite the fact that they had these atlases, and they had some mathematical rules that allowed them to predict what kind of what wavelength they would expect from an element, there were some combinations of lines that couldn't be replicated by any known element on Earth. And so people started wondering, are they due to new elements that we haven't discovered yet? And I'm bringing here the two cases that are the most famous ones. So in 1864, Huggins observed the planetary nebula NGC 6543, which is also known as the Cat's Eye Nebula, for the first time. Nobody had seen a planetary nebula with a spectroscope before that. And what he found that there was a combination of three spectral lines at 372 nanometers, 495 nanometers, and 501 nanometers. And this combination could not be traced back to any known element found on Earth. And so he thought that he had discovered a new element, which was actually given a name. It was called the nebulium. And 5 years later, in 1869, there was a solar eclipse on August the 7th. And two different teams of astronomers took a spectrum of the corona. And they found that there was a green line at 530.3 nanometers that again could not be associated with any element known on Earth. And so they christened another chemical element that was previously undiscovered, and they called it coronium. However, as our understanding of how spectra are created, our understanding of the mechanics of the atom became better and better, we found that this better theories unmasked the familiar faces. So nebulium didn't actually exist. Actually, people found that if they predicted the number of electrons that this element should have, they found that there was no room for a new element in the periodic table of elements. And what they found is actually you don't even need to assume that there is a new element, because that spectrum is perfectly explained by the emission of an oxygen from which you take away two electrons. So you ionize the oxygen twice in very low pressure conditions, so hard to replicate on Earth, and you get that kind of spectrum. Same thing with coronium. Coronium was actually found to be nothing else but the spectral line that you get by ionizing an atom of iron by 13 times, so taking away 13 electrons from the 56 that the atom of iron has. So, okay, this is great, but are we still talking about tester imaging in this presentation? Well, yes, because most of the stuff in the universe, as we know, is hydrogen. Hydrogen has been present in the universe since the Big Bang. It's the simplest of all atoms, made up of one proton and one electron. It cannot be produced by any other, by fusing any other reaction. It's the simplest one. When an hydrogen atom is ionized by radiation, like shine a UV light on a cloud of hydrogen, if the radiation is sufficiently strong and energetic, it will ionize this gas of hydrogen atoms. And ionizing means that we'll strip away some of the electrons from the electron shell of the atoms. Eventually, these electrons will recombine with the free proton to form another hydrogen atom. But when doing so, the electron may find itself initially at a higher energy state than the one that it was previously, because it has received some of the energy from the incoming radiation. And will eventually fall towards what we call the ground state, the lowest energy state, by transitioning into intermediate states. When it transitions from the state associated with the principal quantum number 3 to the principal quantum number 2, it emits a radiation at a very precise wavelength of 656.28 nanometers. And that's what we call hydrogen alpha. And it's one of those of the lines from what's called the Balmer series, that they are all transitions from a higher energy state into the state with the principal quantum number 2. The beauty of this is that most of the universe glows in H alpha when excited by ionizing radiation. So when you have a very hot star, lots of ultraviolet radiation, and around it there's a cloud of gas, chances are it will glow in H alpha. So it makes a lot of sense to image at this wavelength, because we know that we're going to see stuff. But what other interesting stuff is there? Well, it's star stuff, as Carl Sagan would put it. So they are, save for some helium that was created in the Big Bang, all of the other elements on the periodic table are made in stars. So if you are a research astronomer, if you want to study stellar evolution, for instance, looking at planetary nebulae that are one of the stages of stellar evolution, it is probably a good idea to be looking at oxygen 3, because as we know, since the beginning of our history of observing planetary nebulae, we found that O3 was present in those shells. And if we look at the table that I put on the right, these are the relative abundances of chemical elements in the Milky Way, which we consider to be a proxy for the rest of the universe. So hydrogen, of course, takes the cake, and helium is a good second. But then, although it's distant third, the third most abundant element is oxygen. So you definitely want to look at that. Then you have carbon, neon, iron, nitrogen, silicon, magnesium, and sulfur. Sulfur with an atomic number of 16 is not a very widely abundant element in the universe, but it's interesting because it's associated with the later stages of evolution of very massive stars. So red supergiants, when they start forming heavier elements. And there are markers of stellar evolution. These are some of the reactions that you find in the so-called multi-alpha process. So a star like the sun fuses hydrogen into helium. But when you have produced helium, if the temperature is sufficiently high, helium nuclei can fuse and produce beryllium. And if you fuse another helium nucleus with a beryllium nucleus, you're going to produce carbon. And then carbon plus helium, you get oxygen, oxygen plus helium, neon, neon plus helium, magnesium, and then silicon, and then sulfur. And you can continue getting, producing the argon, calcium, titanium, chromium, iron, and finally nickel. And iron and nickel are the last two elements that can be produced in a steady state star, because past the nickel, you need to spend more energy to fuse two nuclei than you get in return. So it cannot possibly sustain a star at that point. And all of the elements heavier than nickel are produced in supernova explosions. So why sulfur? Why is it interesting? And to whom? Well, ionized sulfur is present, as we said, in planetary nebulae, especially when those that are shed by very massive stars. And they need to be big because they need to be hot enough at some point in their life cycle to produce sulfur. And in order to produce sulfur, they must have produced all of the other elements up to silicon to be able to do that. And of course, it's also present in supernova remnants, because a supernova produces essentially everything. It's professional astronomers found that the abundance of sulfur appears to be correlated with regions of compression, like shock fronts in the interstellar medium. And of course, if you are a research astronomer and you want to study the interstellar medium and its interaction with supernova explosion, planetary nebula, etc., this is interesting. But why do we care as amateur for sulfur too? I don't really have a precise answer. Maybe it's because we want to like the Hubble images in SHO palette, and we like to do the same. It's also true that some of us amateur astronomers don't care about S2, and they are perfectly happy with doing what's called bicolor imaging, using just hydrogen and oxygen. So you might have heard about HOO imaging. That's what it is. There's another reason, in my opinion, and it's that if you want to produce a full color image, you need to be able to stimulate all the three types of receptors in the human eye. And those three types of receptors are, well, first of all, there are three, and they responded to red, green, and blue. And so it is convenient to have three different, to capture data in three different wavelengths that have different morphologies, different shapes, so that you can combine them into an interesting full color image. And we're going to dig deeper into this in the second session in 2 months. So are there other interesting lines? Sure, there's a lot of them. For instance, another one that I'd like to see more is H-beta. I remember when I was buying skying telescopes in the late 80s or maybe early 90s. There was every issue had a full page advertising by Lumicon, and Lumicon made and sold H-beta filters, and their claim was I can see the Horsehead Nebula with the H-beta filter. Because the idea was that you would be able to see B33 as a dark notch against the backdrop of IC434, which is a hydrogen cloud. So it will glow mostly in H alpha, but our eyes, of course, are not sensitive to that wavelength at night. But they can see well in the region where H beta is. So if you put a filter that increases the contrast of that line, you would be able to see it visually. From an imaging perspective, it's probably not that interesting. Where there's H alpha, where there's H beta, there's also H alpha. So it's probably going to have the same type of structures, the same morphology that you already have captured in H alpha. And also, we have to deal with what's available on the market. Most commercial narrowband filter sets are still H alpha, S2, and O3. And so we get what we can find. Okay, so we know why we would like to image those wavelengths, but why does it need to be done with a narrowband filter? Can't I just use my RGB filters or my OSC camera? After all, if you capture everything with a 100 nanometer wide filter, you're also going to capture those wavelengths. Why is it important to capture only those wavelengths? And there's a number of reasons for this. For instance, selectivity, the fact that you're going to cut and only see the objects that have that line emission, or almost only. And this gives you also better contrast. The use of narrowband filters give you less star presence. The stars are less, are smaller, are tighter, they are less intrusive on your image. And then there's the reason, which in my opinion is the most important, is that if with a narrowband filter, you are greatly reducing the adverse effect of light pollution. And the narrower is the bandwidth, the greater is the benefit. So I have here a few examples that I'd like to share with you. And I'm going to start talking about the effect of contrast, the effect of narrowband on contrast, detail, and star presence. So if you isolate only one wavelength, you're only going to see those structures that emit in that particular wavelength, or almost those. As we know, there's always a continuum component, but thanks to Alex, we have the mathematical tools to remove them and go back to observing exclusively or almost exclusively that wavelength. The result is that the details, and in particular the edges, become very crisp, sharp. An additional benefit is that since the stars are black body radiators, if you select their light with a narrowband filter, you're going to throw away most of the light of that star. And so the stars, the throughput of the stars, the photons collected by your sensor that come from the stars, will be way fewer than otherwise with a broadband filter. So you're going to get results similar to this. So this is the same object, NGC 281, the Pac-Man Nebula, imaged with the same telescope, but with an OSC camera on the left and a narrowband camera on the right. And the narrowband camera using a 4 nanometer O3 filter, 4 nanometer O3 S2 and H alpha filter gives those nice filaments in the dark clouds that you simply don't see in the OSC camera. And also the stars. In the left image, the stars take take the limelight. You mostly see the stars. And in the image on the right, the stars are not intrusive at all. They don't take away anything from the nebula. They make it actually very legible. Another example is here. This is the famous, I can't remember the catalog number, but it's the Tadpoles Nebula. Again, on the left with an OSC, and on the right with in a bicolor palette. It's HOO, so hydrogen and oxygen. Look at how the two tadpoles, you have to almost make an effort to see where they are in the OSC camera. And they are very contrasty, on the other hand, in the narrowband image. They contrast in color and they contrast in shape. The shapes are very sharp. You can see the body of the tadpole, so to speak, not just the head. Also, look at the darker clouds. You see some details in those wisps around, dark wisps around the dark clouds that are simply not visible in OSC. And again, the stars, there's a big open cluster at the core of this nebula. It's actually the cluster that makes the nebula glow. And it's much more manageable, I would say, in the narrowband rendition. So there is a benefit there in making images that are more striking, in which the contrast of shapes and the contrast of color is much more attractive. Again, I'm talking about aesthetics, not about science here. It's pretty pictures. Okay, what I believe is the real game changer, though, is the reduced impact of light pollution. And this is especially important for urban imagers and suburban imagers. Okay, why is that? Well, nowadays, we all have LED lighting on our streets. Light pollution is essentially broadband. And if you use a narrowband, you cut down the light pollution very efficiently. And I know that some people would object if I say this on cloudy nights, that, oh, you can achieve the same with good gradient management, with gradient reduction, gradient subtraction, you call it, you name it. Well, let's see if that is true. There is a common misconception that I'd like to fight here, is that we cannot image objects that are fainter than the background because light pollution hides your faint object. Well, if you think about it, that doesn't really work that way. Light always adds. So even a faint object would always ride on top of the background light, not under the background. If you have a background sky that gives you one photon per second per pixel, and you only get half a photon per second per pixel from an astronomical object, you're still going to have 1.5 photons per second per pixel if you're imaging the object. So there's always additional light. And it's not just a matter of contrast or saturation either. Otherwise, we would solve all of these problems by doing gradient subtraction and using short exposure to avoid saturation. And we would have defeated light pollution. Doesn't work that way. I think we all know that that's not the right proposition. And I'd like to explain why. In my opinion, why is because the name of this game is a signal to noise ratio, SNR here. So photons are not coming, light is not a liquid. Photons are not coming as a continuous flow, but arrive one by one. They are quanta. And the result of this is that their arrival is described by a theory, a statistical property that has statistical properties of a Poisson distribution. It was studied by Poisson. Rare events behave in a certain way. And so if you have two detectors, like 2 pixels in a sensor, that are counting photons exactly from the same source, at the end of an exposure, we likely end up with 2 different tallies, even in a perfect camera. It has nothing to do with the camera, has everything to do with the nature of light. there will always be a certain probability of getting any non-zero count. And I have here hand-drawn what could be the distribution of photon counts in a typical coming from the background, for instance. You're going to have a mean count for all of your pixels that are exposed to the same light. And this distribution is also going to have a certain standard deviation, certain width. Well, a property of Poisson events is that the standard deviation is equal to the square root of the mean. So if the mean represents the number of counts of photons by your detector, you can expect the standard deviation in this distribution equal to the square root of the average number of photons. And this is a very important property because it creates, we can work this to our advantage. Because it's not the number of photons from light pollution that hides a faint object. It is the fact that from pixel to pixels, there are variations. There's the standard deviation 66 times out of 100, you can expect that the variation from one pixel to the next will be less than one standard deviation. And it's this variation that makes a weak signal undetectable because it's the variation itself is larger than the signal that you want. This is what we call photon noise. Some people also call it shot noise because of a different, by focusing on a different property of what they do. It's nothing to do with the camera again, it's the nature of the photon beast. If you want to see an object, you need to have a signal that's larger than the noise. And I'm going to give you some examples here. This is a simulated examples. Let's assume that I'm imaging a target like the one that I have in the upper left, in the upper right. There's a certain background, and there's a region of my object space that is brighter than the rest. And I'm going to change the brightness of this. If we start with a situation in which I get one photon per second per pixel from the background, and the brighter square at the center only adds 0.05 photons per second per pixel, so I can expect as an average one photon every 20 seconds. At the end of a 600 second exposure, I'm going to have that the mean value, the mean number of photons counted is going to be 600 per pixel. The standard deviation associated with that will be 24 photons. So from one pixel to the next, I can expect 66% of the time a difference of less than 24 photons. And the signal is only 30 photons per pixel. So the signal to noise ratio is almost 1. In this, in the chart on the lower left, I have plotted the count of photons in each pixel along the dashed line. And I don't see the object. I don't see any difference that makes me think, oh yeah, this is the brighter part of this object. It's virtually, to my eye at least, it's virtually undetectable.
Hey, Francesco, on your screen though, you may be showing the right part of the slide because there's at least for me, a pretty clear rectangle there.
You mean, I don't have a cursor here, but you mean on the left?
On the upper right, yeah.
Oh, right, yes. So the upper right just represents what's, let's say, the image space. No, sorry, the object space. So I have there is a difference there. If I look at the number of counts, this is I amplified the difference.
Oh, I got it. Sorry.
But the count corresponds to the actual numbers. So yeah, this one is undetectable if I look at the numbers. Now let's do the same with the larger number of photons. So I have the same background, 1 photons per second per pixel, and I increase the signals 10 times. It's let's say 0.1 photons per second per pixel. With this, actually, sorry, this is a mistake. It was used to be 0.08. And the exposure is still 600 times. So the mean is the same, the standard deviation is still 24 photons. The signal collected from the object, in this case, is 48 photons per pixel. So the signal to noise ratio has become 2. And if you look at the chart on the left, you start seeing that there is an increase around the center. You still cannot really tell if it's how sharp it is. It could be anything. So it's maybe it's on the verge of being detectable. Now let's make it even brighter. This is another example, same background, but the signal from the object is now 0.2 photons per second per pixel. So we have a signal collected by each of the photons of additional signal of 120 photons per pixel. This is 5 times higher than the standard deviation. And at least to me, this in the chart on the graph on the left, this is clearly detectable. You can see that there is a change, a square wave, so to speak. Now, this is great, but we are not in this simulation, right? It's in reality, it's too bad that we cannot just crank up the brightness of an object that we would like to image, just like I did in the simulation. What we can do is to change the other element of the signal to noise ratio. We change the number this is below the fraction sign. For instance, we can turn off light pollution by loading the telescope in the car and driving to the Sierra. Or we could increase the exposure time, or equivalently, stack together multiple exposure. This works, but it takes patience because the signal to noise ratio only goes up like the square of the total integration time. I have hand drawn here what could be the relationship of signal to noise ratio on the vertical axis and integration time. And to me, this is a law of diminishing returns. You have to go, if you want to double signal to noise ratio, you have to quadruple the exposure time. So if you already image for 1 hour, the next big change will require 4 hours, and then 16, and then 64. It quickly becomes unmanageable. But let's see how narrowband can lend a hand. There's another way to decrease the number of photons from light pollution, and it's to use a filter. Of course, we would need a filter that blocks the photons from light pollution and not those from the object of our interest. Well, a narrowband filter does exactly that if it matches the wavelength of the object light. So if you want to image a nice hydrogen cloud and you're using an H-alpha filter, almost all of the photons of 656.3 nanometer wavelength will go through. These narrowband filters typically have a transmission of 19 to 95%, pretty good. But of course, it doesn't work for all targets. It works great for emission nebulae, that could be gas clouds, but also planetary nebulae. It doesn't work for dark nebulae. It doesn't really work well for the reflection nebula, because reflection nebula typically reflect the light of a star. As we know, the light of a star has a black body spectrum. And it doesn't work really well for galaxies unless you want to image the H-alpha regions of that galaxy, or O3 region of the galaxy, because galaxies are mostly made of stars, and stars have a continuous spectrum. However, if the galaxy is close enough, there is a benefit in imaging it also in H-alpha, because it highlights the regions of star formation, the H2 regions. How does our simulation change if I introduce narrowband? So this is just the same slide that I showed you, the one in which I cannot basically detect what's going on in the center by looking at the graph, because my signal to noise ratio is close to 1. Now let's put a 3 nanometer filter in front of my telescope. So instead of collecting 1 photon per second per pixel, assuming that this was done with, let's say, a green filter, 100 nanometer wide, instead of receiving one photon per second per pixel, I'm going to receive 0.03 photons per second per pixel, because assuming that the background sky is uniformly distributed, and it's a big assumption, but let's simplify things, I'm only going to receive 3% of the incident radiation. And I'm also going to reduce a little bit of the signal, but assuming that this has 90% transmission, I went from 0.05 photons per second per pixel to 0.045, not a big difference. But look at the graph, a lot has changed here. And the reason why a lot has changed is that the mean signal from the background went from 600 photons per pixel to only 18. It's 3%. As a consequence, the standard deviation also went down, and it's now just 4 photons per pixel. The signal, on the other hand, went from 30 photons per pixel to just 227, did not go down by much. The signal-to-noise ratio has increased a lot. We went from a signal-to-noise ratio of 1 to a signal-to-noise ratio of 6, which makes this object very detectable, as you can see. So the big benefit of doing narrowband imaging, especially from light polluted areas, is in the signal-to-noise ratio. If I compare a narrowband line filter to a broadband filter, the narrowband filter cuts the signal from the background by a factor of the ratio between the bandwidth of the narrowband filter divided by the bandwidth of the broadband filter. Then the associated noise will be reduced by the square root of this ratio. Or if you prefer, by inverting the fraction, if the signal from the object is transmitted entirely, let's say 95% of it, the signal-to-noise ratio goes up by the inverse of those factors. Assuming that you start with a 100 nanometer filter and you end up with a 5 nanometer filter by switching the broadband with the narrowband, the signal-to-noise ratio increases by 4.5 times. That's pretty significant. So now that we have an understanding and we have our appetite whet by this, what do we need to do to capture narrowband data? Well, you need to, inevitably you're going to have to get some filters. You're going to have to spend some money on filters. There is one traditional way that has always been around, and it's to use what's called a monochromatic camera. It's actually, in my opinion, a misnomer. It should be called a panchromatic camera because it doesn't see only one color. It sees all colors, but sees them identically, so it doesn't differentiate between colors. And then you have in front of this panchromatic camera a filter wheel, and in the carousel of this filter wheel you put the typical 3 filter H alpha, O3, and S2. But more recently, there's been an alternative. A number of multi-narrowband filters have hit the market. I believe that one of the first ones, primarily the most famous, was the Radian Triad. These are filters that transmit multiple narrow wave windows of the spectrum. And the idea is to use them with one-shot color cameras or even DSLRs. The filter is designed so that the windows that will be transmitted are somewhat compatible with the transmit windows of the Bayer matrix, so that you're going to get some signal in the red pixels, in the green pixels, and in the blue pixels. And so you're not wasting your color sensor in the same way that you would if you just put a single narrowband filter in front of it. There's also a reason to use them with monocamera as an alternative to luminance, to the luminance filter. So luminance is a filter that cuts everything shorter than 400 nanometer and typically longer than 700 nanometers. But instead of using that, you could use a multi-narrowband filter if what you're trying to image, of course, is emitting light in those wavelengths. There's also another benefit of using those, in particular using a monocamera with narrowband filters, is that any chromatic aberration that you may have in your system, it becomes almost negligible, because each time you're going to image one very narrow window of the spectrum, so there will be no significant dispersion inside that, and you're going to refocus each time, so everything will be sharp, although they are not sharp at the same time, because you're imaging three in 3 installments, essentially. These are just some examples of some manufacturers of a narrowband filter that you can find. Probably the 2 best, the 2 that are considered the best from a quality perspective are Astronomy and Chroma. They are also the most expensive. Astronomic is another very reputable brand. This is German. Baylor is also German. They make narrowband filters. They made a new series that came out last year. There's been some controversy about those, especially if you image with the fast ratios. I use them, they work for me, but your mileage may vary. And of course, there are also other players on the market like Optolong that makes a lot of optics for amateurs. And also Antlia, I believe, has a set of 3.5 nanometer filter in SHO. And I'm sure that there are other ones too. These are also some examples of multi-narrowband filters. I already mentioned the OPT triad, sorry, the Radian/OPT triad ultra filter. Despite the name, it does not transmit three sections of the spectrum, but 4. So there's S2, H alpha, O3, and H beta. So in this way, they try to cover all of the 3 Bayer sensors, Bayer filters. There's Optolong has always been present with their L Extreme filter. So you see the name recalls the fact that you can use it as a luminance substitute. And has pretty narrow bandwidth, as you can see from this chart. And more recently, IDAS has come out with some multi-narrowband filter, although they are not as narrow as the other ones. They try to tell you that it's a benefit because in addition to capturing H alpha, you also capture the ionized nitrogen. And in addition to capturing O3, you also capture H beta and the second line of O3 at 495 nanometers. But of course, the price that you pay for that is that you also capture more light pollution. So there's a trade-off here. There is, however, one drawback in all of this. And the drawback is that our narrowband filters are so effective in cutting down the background signal that the magnitude of the photon noise, as we saw, also goes down. And it may go down to the point that it becomes similar to the magnitude of the camera's inherent readout noise. And this is a problem because it's noise adds, although it doesn't add algebraically, it adds in quadrature. But you don't want to be dominated by the camera's readout noise. You want your images to be dominated by essentially photon noise. And there are 2 things that you can do to achieve this. You could decrease the read noise of your camera, which is possible in to some extent, because typically most CMOS cameras and also CCD cameras, by increasing the gain, the read noise goes down. But 2 things. One thing it's important to be careful about is that watch your well capacity. So most cameras, actually all cameras, have the largest full well capacity at low gain, where the read noise is higher, and the full well capacity decreases proportionally as you increase the gain. The other thing you can do, although it seems counterintuitive, is to increase the photon noise. Now, why on earth would we want to increase noise? Because actually you're not increasing noise, you're increasing the signal, and noise goes up as a consequence. And increasing the signal in this case, it means that you increase the exposure time. So you expose for a longer time. These are 2 charts that I took from the ZWO website. This is for the ASI 2600 mm. And you can see the top chart shows the full well capacity as a function of gain. And you can see I increase the gain and the full well capacity goes down. And that's kind of inevitable. What's interesting is the bottom chart. There's like many modern cameras, there is one critical value of the gain parameter that triggers the high gain mode or something like that, and creates this sharp step, and the readout noise goes down starts from 2.8 electrons per pixel at gain 99, and it goes down to 1.45 electrons per pixel at gain 100. That's a huge change. Of course, you may want to say, okay, but why should I stop there? I crank the gain up to 450, and when I have 1 electron per pixel of read noise. Yes, true, but you're only going to have a few hundred electrons as a full band capacity, so you're going to reach saturation very quickly. So be careful. The other aspect, so we said this was about gain. The other parameter that we can play with is exposure time. You might have heard that with all the CCDs cameras that had very high read noise, like 10, 15 electrons read noise, narrowband used to require very long sub-exposures, up to 60 minutes. Now this, to me, reminds me of the days of film astro imaging, in which you expose for such a long time that if an airplane or a satellite crossed your field, you started swearing because you just had wasted an hour. But low noise CMOS cameras have changed this. Nowadays, with the modern CMOS cameras, the readout noise is so low that less than 5 minutes are sufficient to swamp read noise, even from even from not Bortle 9. You can do it from Bortle 5 or Bortle 6 and still swamp noise. And this also brings me to another point that is worth mentioning. So these are a few examples that I'm going to give you. But the question that I want to answer is, if you want to take full advantage of, is it worth imaging in narrowband from a low Bortle site? Is it worth driving to Pinnacles and imaging in narrowband? And in order to answer these questions, I'm going back to one slide, and I want to show you 2 charts. Now, this chart is actually an analog exposure calculator. It's called a Nomogram, and it's something that I developed. And it allows you to estimate the minimum exposure time that you should use based on a series of parameters. So it needs to be read from left to right. So you start, this is an example for Bortle 7. So you start plotting a line that goes from the point that corresponds to the radiance of your sky in magnitudes per square arc second. Now, I am on Bortle 7, and my sky is typically, when I measure it with my SQM, I read 18.5 magnitudes per square arc second. So my line goes from this point, goes through the point that corresponded to the F ratio of my telescope. And then I keep on drawing with the pencil and the square and the straight edge until I meet this vertical line. Then from this point, I draw another line that goes to the point that corresponds to it's called the spectral efficiency of my filter. And it's the fraction that is essentially the bandwidth of my filter, delta lambda, divided by the central wavelength of my filter. This is an example calculated for a 5 nanometer H alpha filter that has a spectral efficiency of 0.075. And again, this line will hit a point on this vertical line. And I'm going to draw another line going through the point that corresponds to the pixel size of my camera. And this is going to land somewhere on that scale called phi in photons per second. And that is the estimation of how many photons per second per pixels I'm going to receive from the background sky. Then I plot yet another line through this scale with the eta parameter, which is the quantum efficiency. In this case, I estimated 80% quantum efficiency. This is calculated for the ASI 2600. And I see that this corresponds to receiving in each pixels 0.2 electrons per second. Finally, the last step is to draw the final line from this point that we just calculated through the point that corresponds to the read noise of my camera. Let's assume that I set my camera for gain 100, so my readout noise is 1.5 electrons, and I get to the final answer. The minimum exposure time that I want is about 1.9 minutes. So from Bortle 7, 2 minutes are sufficient. What if I go to Pinnacles, Bortle 3? Things change. So Pinnacles has a 21.5 magnitudes per square arc second. So if I redo all this geometrical construction with pencil and straight edge, I get that I should expose for 30 minutes each sub-exposure if I want to reap the full benefits of the increased signal to noise ratio that I can get from that sky. And so by this, I mean that the ratio of the brightness of the Pinnacle sky and the Mountain View sky is 1:20. So it means that if I expose for using this suggested 30 minutes, I'm going to get a signal to noise ratio which is 20 times better than I can get from Mountain View for the same total integration time. So is it worth doing that? Well, it depends on many things. It depends on whether your mount is up to it, whether your mechanics are up to holding a 30-minute exposure without a differential flexure, or if you use a OAG, if you're probably in a better place. Is your guiding up to this task? But in general, I would say, even if you don't do this 30 minutes, if you just do 10, yeah, you're going to give up something, but it's much better to have some data that have no data because something went wrong in between. So my final message, and this is my last slide, is that don't sweat too much over it. Just get out and start imaging. And you have 2 months to capture all the data that you want. And in 2 months, we're going to talk about how to process the data. Thank you very much. Is there any questions that I can take?
Hey, sorry, yeah, I forgot, I couldn't find my unmute button, but please, questions for Francesco.
I have a basic question about physics, which is that hydrogen alpha is a transition between the N3 to N2 line, right? What
Right.
happens to the N2 to N1 line?
It's not in the visible spectrum.
Is it brighter in its wavelength than the N3 to 2?
It's I don't know about brighter, but it's in the infrared.
Okay.
You mean the UV? It's higher energy, it's a bigger.
Sorry, higher energy.
So it's a UV line. And so, yeah, that would be the primary line. That is a big line for radio, I mean, not radio, but for UV. But since we're talking about visible light,
Great presentation, Francesco.
Thank you very much, Rick.
Francesco?
Yep.
Do they make narrowband filters that screw on the front of camera lenses, or where would you place them?
Yeah, they do.
It's a great question. Lumicon used to do that. I remember that Lumicon had H-alpha filters that had the 49 millimeter standard thread for photographic lenses, and also 52 millimeters. I believe they went all the way up to 72. That was extremely expensive. Nowadays, I haven't seen any. However, both the Chroma and the Baylor, they make filters in the, I believe, in the square 65 by 65 millimeter format that you can put in a filter holder that you then screw in front of your camera.
I understand. So it's a square 65 millimeter square, and like I used to do 50 years ago, when I used Ratten Gelton filters, you drop that in a square in front of the lens.
So back, given that you mentioned years ago, I was doing, I didn't have an H-alpha filter back then. I was using the Technical Pan 2415 film that was very sensitive to red. And I used the Ratten 29 filter as a makeshift H-alpha in front of the camera.
Yes.
There's also, I remember Astronomic used to make clip-in filters that actually fit in front.
Oh yeah, that's right. Yep. So those are, I had one for my Nikon. The problem of those filters is that they are tailor-made for that particular camera model. And when you replace your camera, you're basically going to have to replace the filter as well.
What focal length camera lens do you typically use for getting those nebulae?
So I'm actually using my telescope, and it's I should remove my blurry screen. Better. Yeah, telescope is here, so you see the camera.
I do indeed. It's a beautiful instrument, but given that I'm rather spending my money on camera equipment, it's either one or the other.
Right. So for one lens that I personally don't have, but has become very popular in recent years, is the Samyang or Rokinon 135.
I have one.
Oh, perfect.
It's a manual focusing lens, and I have it in Nikon F mount.
Perfect. So you can, there's one thing that you want to be careful about. That is a very fast lens, f2. So if you can put the filter in two positions with that lens, you can put it in maybe not with a DSLR, but with an Astro camera, you can have a filter drawer and put it between the lens and the camera.
Yeah.
If you do that, you need to buy special filters and they have the central wavelength pre-shifted for very fast F ratios. Because because the bandwidth, the central frequency is calculated based on the cone formed by the light rays when they meet the sensor, when they meet the filter actually. But if you put the filter on in front of the frontal lens, then the wave is a plane wave at that point. So perfect. You don't have any problem with, and you don't need to pre-shift.
Right.
The drawback is that any error that on the wavefront that is introduced by the filter will be amplified on the focal plane. But if the magnification of the lens is not too high, like the 135mm one, you should be still in good shape.
Thank you very much.
Absolutely.
Do we have any more questions for Francesco?
Sorry,
Francesco, sometimes with these narrowband filters, I've had reflections inside the refractor. Do you have any comments about that and what to do about it?
So yes, there are reflections are a problem, and this seems to be one of the cases in which the rule by twice applies. The people who use expensive filters like Chromas and or Astrodome in general don't have these problems. And of course, no manufacturer tells you there's, but there seems to be a correlation between how the type of multi-coating that they put on the filter and how big, how strong is the reflection that you're going to get. Apparently the optical filters were pretty bad, but they recently changed. They improved a lot. Beta was also very bad, but I have the latest generation Beta filters, and really I have no reflections even in a relatively bright star. I did a 10-minute H-alpha exposure on the neb, and there's no reflections actually. But yeah, it's a problem. And some people have noticed that the type of coating that they put on the filter is not the same on the front side and the back. So if you have a strong reflection, it may be worth trying to flip the filter and see if it's any better on the other side.
Paolo, did you have a question?
No, not a question, but a side note about what I think Alan before was asking about the photographic lens to use. I think that the sweet spot is also between 300 and 400 in my experience. There are let's say beautiful target in the 135 or 150, but if you want to do some nice nebula or something like that, you have to have a longer focal length. But anyway, 300 or 400 tele lens is more than perfect. Not as impossible.
An interesting project that I have on my hands is to reuse for astronomy this beautiful Pentax 135 millimeter lens from the early 70s. Used to belong to my father, and of course nowadays this is not an apochromatic lens. It would have a chromatic aberration in full color, but my idea is to use it in narrowband, and so I want to put some focusing mechanism that would turn this helicoid to refocus when I switch filters, and so I can have perfect focus at all three wavelengths. And I hope I can get there.
Yeah, it's feasible.
So I'm taking it that what you're doing is that you're taking a series of exposures with one filter, then even though you're leaving the camera on the tracker, you're then replacing the filter with the next filter, taking exposures, then you replace it with another filter.
Yeah, and this is in a setup like the one I have, this is automatic because the filters are mounted in a carousel in front of the camera, between the camera and the telescope essentially. And there is a stepper motor that controls this carousel. So the computer tells the camera, now go in H alpha, and the camera goes in H alpha. And the computer knows that the program has stored in its memory what is the difference in the focus point when I switch from H alpha to O3, and tells the focus motor to move to compensate for that. So it's you can with this level of automation, you can, if you want, you can take 20 images one filter and then 20 in another one and then 20 in the third one, or you can do 111, 111, 111 and change every time, because you don't need to refocus. Everything is, you can predictably and reliably automate that part.
And we can discuss what is the best strategy depending on what is the say the environment. If you have the moon or something like that, probably it's better to do a 111 or 222 instead of 20 20 20, because the gradient will be different.
Yeah.
And there's also for those of us with reflectors, you may not have a focus difference between your filters.
Yeah, even better. If your filters are parfocal.
Sometimes depends from of the filter also. If you mix different filters, sometimes you have different focal point, because the filter are different in thickness.
Right.
That's a good point. One question that I should probably have added to my presentation is, can you mix different filters from different brands? Yes, of course. The filter, what counts is only the wavelength and the bandwidth of the filters. However, if you do that, you may need to be prepared for some more refocusing, because if the filters were cut from the same piece of glass substrate as the same thickness, they will likely be parfocal. So you are not going to need to refocus. But if they come from different manufacturers, they likely have different thicknesses, and maybe the glass has different refractive index. So you will want to verify.
In my experience, Astrodon and Chroma are parfocal.
Yeah.
At least the one that I have.
Everybody says so, that if you can spend the amount of money that they want, it's definitely worth it.
Yeah, especially Astrodon is virtually disappeared from the market in this moment. Oh. At least up to 1.5 months ago when I checked.
So we're going to see them in auction houses, I guess.
Mm.
But that's when I first started imaging, that was a big misconception I had. Like, I bought these so-called parfocal filters, and then but I used them with my refractor, and the filters were parfocal, but because the refractor, bottom line was despite the way they're advertised, you do have to change the focus between your filters. And I
If you
did,
have a Ricci Chrétien, probably not.
right, no, I'm saying for refractors. Now reflectors, it's another story. Now, Nick has a comment. If you want Astrodon, use iTelescope for free.
Yeah.
All right, any other questions? All righty then. Well, thank you very much, Francesco. We look forward to hearing from you in a couple months. Everybody will take all their narrowband images, and maybe you'll give us some practice data to play with before that
Yeah,
that
that's the idea.
processing section. And then again, next month, we have a talk. You were talking about making a focuser for your lens, and Julian will talk about that and other maker projects next month. And thank you very much, everybody. Please unmute and give Francesco a hand.
Thank you very much.
Yay. Bye-bye, everyone.
Bye, everybody.